great to get to talk about impact cratering. As Anya mentioned, I'm a staff scientist at Johns Hopkins, and I'm also a project scientist on Dragonfly. And I'm a geomicrobiologist, and I work primarily on the biology related to impact cratering and also hypersaline environments. So when we think about impact cratering, we normally don't think about the origins of life on Earth, but there is a very close tie between those two ideas because of when impact cratering was occurring at higher frequencies during the evolution of life in the early Earth. So we believe that life evolved on Earth sometime prior to 4 billion years. There is increasing evidence for life that is being preserved in the rock record at 3.8 to 4.1 billion years. The question is that when we look at crater counting through lunar impacts, we know that impacting was about 10 to 20 times more common at this time point than they are now, regardless of whether or not you subscribe to the late heavy bombardment or sawtooth model or what have you. So the question is then, how did life evolve at the harshest, most inhospitable time in Earth's history? So some scientists have looked at this and said that, okay, well, then this must have caused an annihilation of the earliest ecosystems by large asteroids impacts. And so this is papers by Norm Sleep. And then others have also taken that to indicate as a reason for why we have sort of this idea of hyperthermophiles as our last universal common ancestor. So if you look at phylogenetic trees like this that are made looking at the 16S ribosomal RNA, which is the most one of the most ancient and most conserved informational polymer for life, and you treat out all like this, it shows all of the earliest common ancestors are all from thermophilic or hyperthermophilic environments, so like really warm temperatures. And so the idea is that, well, okay, there was a lot of impacting occurring at this time, so a lot of energy, so environments were very, very hot, and this could have created this could be why that we have hyperthermophiles as our last universal common ancestor. And it's a kind of bottlenecking event. So maybe there were other types of life, but only the hyperthermophiles survived, and then life proceeded from there. There are alternative hypotheses, though, and that is looking at impacts as friends rather than as frustrations to the origins of life and life in general. So this is from work by Abramov and Moises, and they looked at modeling different types of impactors into Mars. This is for Mars, looking at surface temperatures at 1 degree Celsius and surface temperatures at minus 63 degrees Celsius. And they also went with either a sawtooth late heavy bombardment, which are these bottom two figures, or a classic late heavy bombardment. And what they found is that at no point during any of these impact events, regardless of the frequency that was occurring, did the surface temperatures get to a point that it would have sterilized the entire surface of the planet. And the same could be held true for Earth, is that at no point was it so hot that you would have sterilized everything. So this idea of it as a frustration for life maybe doesn't hold. And what also occurred is that because there was so much impacting occurring early on in the evolution of the Earth, is that it actually extended the habitable zone of the planet, because you're fracturing the subsurface of the planet and creating more habitable area. And so the hypothesis that I subscribe to, and what I'll be talking about today, is looking at impacts as friends. So they're great because we have energy input on the scale of thousands to millions of years. We get things occurring during the impact, such as flash serpentinization, which generate methane and H2 gas, which are really great for microbial organisms that are not using light energy for metabolism. They generate clays and impact glasses, which I'll get to a little bit later about why that's great. It causes this brecciation of the subsurface, as I mentioned, and also it's a concentration mechanism. So I'm sure a lot of you are familiar with the idea that maybe life originated in the ocean near hydrothermal vent systems. But the problem with this is that it lacks a sort of concentration mechanism. How do you concentrate life and the ingredients for life in an ocean environment? Whereas if you do it on the surface inside a bowl-shaped depression of an impact crater, it's a much easier mechanism. We also have a mechanism for dehydration and evaporation, which is something that's necessary in the construction of RNA from the prebiotic precursors. So when we're looking at the lifespan of an impact crater from a geobiological perspective, we look at it for three phases: the thermobaric phase, which lasts from seconds to hours; the hydrothermal phase, which lasts from weeks to hundreds of thousands of years; and then finally the post-impact succession phase, which lasts from hundreds to millions of years. I'm just going to focus on the first two just for the sake of time, but I'm happy to take questions about any of these things. So the thermobaric phase occurs in that initial contact compression, excavation, modification phase. What's important during this phase is that what you're doing is you're taking a rock that looks like this and you're shocking it. So you're creating porosity. So this is an unshocked sample. You go to medium shock, moderate shock, so maybe 30 gigapascals. This is about 50 gigapascals of pressure. And then finally, when you get up to 70 gigapascals, so looking at panel F here, you basically turn the rock into Swiss cheese. You're creating an incredible amount of porosity in these samples. These reach the porosity of pumice, and so some of these samples can actually float. This is great from a microbial perspective because when things get tough for microbes, they tend to go inwards. And we have evidence for this from the dry valleys of Antarctica. So there really is no surface biology to speak of in Antarctica, like in the dry valleys. But if you look within the rocks, that you'll find that's actually not true. They're there, but they're hiding. And that's because this environment is incredibly detrimental to life. But the rocks provide an incredible habitat that is more temperature stable, keeps in moisture, traps nutrients, is protecting from UV radiation. And so you get these coherent bands of microbial growth. So you see here the black and the green. The black is providing the UV quenching layer. And these organisms are surviving and persisting within this incredibly harsh environment. And so there's different types of microbials. These are called endoliths, and the name changes depending on how exactly they've made it into the rock. But this is a common strategy that microbes use here on Earth. And so the idea is that, well, the impact event, though detrimental at the time to any existing life potentially, does actually create habitat. And these are novel habitats within rocks that wouldn't have hosted these microorganisms in the first place. So this is an example of impact breccia from the Houghton crater in Devon Island in the Canadian high Arctic. And you can see here, right beneath the crust is this coherent green layer you can see here, and also again here, where you've got microorganisms that have colonized these rocks that previously had no habitat prior to the impact event. And so as I mentioned, you get increased porosity and permeability, greater translucence, moisture, UV shielding, and accessibility to nutrients. And so you see changes in the microbial population as you move through shock. So if you look at unshocked samples versus high shock, you can see there's a huge difference in the number of phototrophs, for example. That's what this graph is dealing with, and in the numbers and types of phototrophs that can inhabit these types of samples. And so these are photomicrographs of SEM micrographs, apologies, of microbes that have either been fossilized or were preserved inside these impact shock lithologies. We also get the creation of impact glasses, and these can also serve as viable habitats for microorganisms. This is work by my colleague, Haley Sapers et al. 2014, looking at impact glasses from the Reese crater in Germany. And she found tubular features that look very closely similar to those that you see in basaltic glass and ophiolites, where microbes have burrowed into the glass because glass is amorphous, so it's easier for them to break down, and they can get all the nutrients that they need from this type of system. So seeing glasses is always a really good thing because microbes have a much easier time making a habitat within a glass than they do of regular rock. And finally, the subsurface, as I mentioned, is a created habitat, a generated habitat through impact cratering. So you can see here's the model from LPI of one of the craters on the moon showing what the subsurface might look like due to the size of the impact event. So you can see the radial concentric fractures and how far down into the subsurface the subsurface is disrupted. So at Houghton, for example, what I was just talking about here, these samples were excavated from down to 2 kilometers beneath the Earth's surface. So you can get an idea of exactly how far the Earth's surface is going to have been disrupted and how much habitat could be created. A really great paper to read if you are interested in looking at more about this is by Coquel et al. 2012, looking at the Chesapeake Bay impact crater. So they did boreholes in the central part of the crater. And what they found when they did microbial enumerations here is that from above the crater, enumerations start to drop off and go to 0 as you increase with depth. So at about a kilometer down, you start to not see any life whatsoever. And then you see nothing. You have granite blocks. And then what happens is when you get below where the impact event happened, so down around 1,500 meters, all of a sudden you have myology again. And that is biology that exists there that permeated downwards because of the impact event. And these organisms are still persisting today, even though they do not have a direct connection to the surface. As we proceed to the hydrothermal phase, after the crater has cooled down to the point where water is no longer evaporating, this will form in any body that has any kind of subsurface water, whether it be meteoric or ice-based, and the duration of this will vary. I'll get to that. So actually, okay. And the duration of this will vary from on the scale of thousands to millions of years. And so when you look at an impact crater, because you're brecciating the subsurface, what you get is expressions of hot springs along the radial faulting, the radial and concentric faults. And you also get it in and around the central peak area because you're bringing up all that incredibly hot material. You also have circulation occurring underneath the melt sheet and in and around the melt sheet as it continues to form. And so there are multiple craters on Earth that have been identified as having hosted hydrothermal activity. And as I mentioned, the Reese crater in Germany is one of them. And then we have the Houghton impact crater up here in the Canadian High Arctic. And so as I mentioned, the duration can differ significantly depending on the size of the impactor. So Sudbury is the high end of this range. So the Sudbury impact crater no longer looks like a crater due to a lot of morphological changes in the region. But this was an incredibly huge impact event. And so we think that hydrothermal activity persisted on the order of 1 to 2 million years. On the other end of that is Lonar crater, which is the crater we know as the lower bottom end of what's capable of generating hydrothermal activity. So this is quite a small crater, less than 2 kilometers across, located in India. And it probably had hydrothermal activity on the order of about 1,000 years. The Houghton hydrothermal system, as I mentioned, is quite extensive and it's one of the best preserved in the world. So this is research that's been championed by Gordon Osinski. So you can check out his papers, starting with this one in Meteoritics and Planetary Sciences. But all of the red dots that you see here, the red dots and stars, are all evidence of hydrothermal deposits within the crater. There's also potential evidence for microbial activity within these hydrothermal deposits, which is the only evidence we have for microbial activity during the hydrothermal event phase of an impact crater on Earth. And that comes in the form of the sulfate fractionation of the pyrite and marcasite that are found in the crater. So basically, if you're not familiar with sulfur fractionation, this is delta 34 sulfur. And the max amount of non-biological fractionation you can get is a depletion to about 20 weight percent. But what they're seeing in both the pyrites and the marcasites is a huge amount of fractionation, which could only have been supported by microbial reduction of sulfate in the system. And so there's good evidence here that that microbes were active in this system during the hydrothermal phase of the crater. And so the question becomes is that if we know that this could have been good on the Earth, could it have been good for Mars? And as the last talk also intimated, is that there is a huge expression of impact lakes on Mars. This is work by Livio Tornabini from 2013, who mapped out the association of megabreccia with hydrated crustal and stratigraphic silicates and located quite a few in the region of Nili Fosse. Toro crater, for example, is one of the best examples on Mars, showing the expression of hydrothermal deposits, where you see these mound formations, which mimic quite clearly what we see here on Earth. So as I mentioned, there are a large expression of crater lakes on Mars. There are about 425 paleo lakes identified, many of which are closed basin lakes. So these are areas where there likely were hydrothermal systems prevalent for thousands of years at the minimum, which then formed a impact crater lake environment. When we move beyond the inner solar system and our terrestrial planets, things become very interesting when we start thinking about impact cratering onto ocean worlds. And so the usual suspects that we like to talk about are Europa, Enceladus, and Titan. And these are interesting considering the amount of water that they contain. So Europa has 2 times that of Earth's ocean. Enceladus, even though it's venting out space, actually only has a very little amount of water, but Titan has 14 times the amount of water that the Earth does. And so the question becomes is, okay, what happens when you have an impact event into this type of system? The problem with the origins of life or the existence of habitable environments in these types of environments is that is a mixing between the surface oxidants and the ocean reductants, because you need that redox couple to generate life. You need the movement of electrons. And so we don't know how thick or thin the ice shells are. On Titan, we don't know if it's 50 kilometers or 200 kilometers thick. We're hoping it's thinner, because when you move to a thinner shell model, then you have this opportunity for your surface and your ocean to mix. And so this is a really cool study done by Bob Pappalardo, looking at Manon crater on Europa. And basically what you need to get out of this is that over time, this melt pool that formed underneath Manon crater eventually drained the ocean. So J and K here is what you're seeing, is that melt pool dipping down, eventually migrating and mixing with the subsurface ocean. So there is evidence that this could happen. On Titan, we do see evidence of impact cratering. So for example, we've got Selk crater here, which is highlighted. And then on the lower quadrant here, this is Minerva crater, which is one of the largest on the planet, or sorry, on the moon. And Titan is one of the reasons I think of as planet is one of the largest moons in the solar system, second to Ganymede. So Titan is incredibly interesting because we have this decoupled outer shell. We have a water ice bedrock, and then we have surface expressions of methane in rivers and oceans, or rivers and seas rather. So this brings me to Dragonfly, which is the project that I'm working on as project scientist. This is a mission to Selk crater on Titan. And this is Selk crater here, and then you can see here's the crater and our approximate landing ellipse. And then we will be launching in no earlier than 2028 to land in 2035. And the mission is to understand prebiotic chemistry, search for habitable environments and biosignatures. This is the suite that Dragonfly will be carrying. So it's a camera suite called DragonCam, run by Malin Space Systems and APL. DragMet, which is a suite of 15 different geophysics and meteorology instruments. Dragons, our gamma ray neutron spectrometer. Draco, which will help acquisition of surface samples, which is being made by Honeybee Robotics. The DRAMS mass spectrometer, which is headed by Goddard Space Flight Center and Kness. And then we also have science investigation on the aeroshell called DREAM. And if you're more interested about finding out more about what the science goals are for Dragonfly, I encourage you to look up this paper by Jason Barnes et al. 2021 in Planetary Science Journal, where you can learn about what our science goals are. And basically, the reason that we're so interested in impacts, especially on Titan, is this idea that on Titan here, we have the ice crust, we have ammonia, we have methane, nitrogen, we have simple and very complex organics. And so if you have a projectile into this type of surface with a water rock bedrock, what does that mean for the potential origins of life and the potential generation of habitats? Can you do things like complex hydrogen cyanide chemistry to generate amino acids, purines, pyrimidines? Even though the surface temperatures are quite cold, do the impact events cause the creation of a hydrothermal system or melt pool on timescales that would allow interesting types of more complex endothermic chemistry to occur? So I'm going to leave you there. I realize this was a lot of information in a very short period of time, but I'm very happy to talk with anyone here, take questions now or talk with you offline. I should mention that all of the impacting work that I participated in is with my co-authors, Gordon Ozinski, Haley Sapers, and Charles Kukel. And of course, a lot of this work is done with wonderful co-eyes investigators and students, and that the projects that are funded by NSERC, NASA Roses and the Beringer Award. Thank you very much.